So first I want to thank Professor Wing-Mei Hu for allowing me to speak to you. It's certainly an honor to be in a room with the next generation of scientific computing, so hopefully you'll find this talk valuable. As you can see, the title of my talk has to do with computational fluid dynamics on graphics processing units. After speaking with some of you on Monday and before, I know that a lot of you are working on this application. Even if you're not, I think this talk is going to be valuable because it's not so much on fluids as it is on a general algorithm to solve linear, nonlinear, partial differential equations. So whether your application is physics, astronomy, engineering, hopefully this will give you a nice template to use for your application. So in the spirit of that, I decided to make the entire talk one long example, essentially, just sort of to walk you through the step-by-step process. When we started this, we decided that I needed to start with a very simple example, something that I could allow myself to walk before I run, as it were. So this is what we decided to do. I call this a CFD problem, but I guess it's really a heat transfer problem if you're technical about it. It's just a two-dimensional problem, and it's steady-state heat conduction. So the problem statement is the following. We have a unit square, this is 1 by 1, and it's temperature 0 on the left, right, and bottom sides, and non-dimensional temperature 1 on the top. And that's it. So, yes? Yes, these are hard boundary conditions. Yeah, exactly. So we're not using von Neumann boundary conditions where it's a gradient. These are just the value of the dependent variable itself, so that's held. And because the reason being it's an elliptic PDE, so we can specify just the value of the dependent variable along the contour of the surface, and that's an appropriate boundary condition. So with this problem, this is the governing equation. So you can show that the energy equation reduces to this, and it's just the Laplacian equation. That's all it is. The Laplace equation equals 0. So this is why this talk is also going to be general, because it has a physical application, but it's also solving a linear second-order PDE that's homogeneous. So with that, now we go through discretization of the solution. So as far as the discretization, we use the finite volume method, which is conservative. Some of you may be familiar with that. So therefore, in each of the grid cells, the temperature will be self-centered. Now for the iterative solver, and this was an important choice. I experimented with different types of iterative solvers. I initially started with the Jacobi algorithm, which has, as some of you know, a very bad convergence rate. We decided to go with the red-black Gauss-Seidel solver, which is parallel. More on this later, but I'll give you just a general introduction. This is the general Gauss-Seidel algorithm, and some of you have probably seen this. It's the sum of the products of the coefficients, which are derived from the finite volume method, and multiplied by each of the temperatures. And note that these are in the cardinal directions. I'm using local support, so it's simply north, south, east, and west, and the point itself. It's a basic 5-point stencil, so it's pretty much as simple as it gets. And where a sub p, the divisor, is simply the sum of the coefficients. Now, for the SOR, or successive over relaxation, which we use to accelerate convergence, and probably you guys have learned this in any numerical analysis class you've taken, it's the accepted value is taken to be a weighted average. So this is the calculated value from here, from Gauss-Seidel, weighted with the value of the previous iterate, and that's equal to the next accepted value. And the omega that I use, the relaxation parameter, needs to be, if it's for over relaxation, needs to be between 1 and 2. In this case, I chose 1.85, which gave fairly good convergence. There is an optimal, by the way, relaxation value, but I didn't use that. I just experimented. So now, red-black. Some of you may be familiar with this. In red-black, as opposed to regular Gauss-Seidel, we color the grid. And the name of the algorithm comes from the checkerboard. That's what it's inspired by. We take the grid, and these are internal cells. I'm ignoring boundary conditions. These are the cells I'm actually going to solve for. Use a staggered color pattern. And it's called Gauss-Seidel. The name's a bit misleading because it's technically two Jacobi sweeps. If you're familiar with the Jacobi algorithm, where we take everything at the current iterate, we do a sweep on the red cells as purely a function of the black to advance from one time level to the next, or one iteration to the next. And then we do another Jacobi sweep on the black to advance that to the next iterate. So, and I kind of outlined this here. And that's all it is. It has a really good convergence rate. But my reason for choosing this is because it's parallel. It must be parallel in order for this to work on the GPU. You'll see why later as I get further into the algorithm. But now I'm just giving you sort of an introduction. And here's a graphical representation of the 5-point stencil that I was discussing. And the local support is the cardinal compass directions, north, south, east, and west, and the point itself. So developing the CUDA algorithm. So now I get to share with you some headaches that I had and some issues that you're going to have to deal with when you develop your own algorithm. I experimented with various memory models. And by that I mean, do I use constant memory? Do I use shared memory? Do I use global memory? What's the right thing to use? Initially, in my readings, I discovered that shared memory was faster, since the reads per iteration will be computationally less expensive. By doing that, and this is what you'll find if you're going to solve a problem similar to this, it reminds me of MPI, in that the blocks act as separate CPUs. And by that I mean it's like doing a domain decomposition, where for each block in the GPU grid, that would correspond to a subdomain in your physical grid. If you do that, then you have to handle the local boundary conditions. So you have to find a way to load from global memory into the local shared memory for each block the halo of cells surrounding each subdomain, just like an MPI, where you have separate subdomains, and then you have to isolate the boundaries and then transfer those boundaries with an MPI call. So it was actually slow. And at least in my experience, this was slow. And the reason is because of the conditionals, using if statements. I found that if statements were extraordinarily expensive on GPUs, and I decided to trash it, and I went another way. And the way that I went was using global memory. So this memory, from this memory, each of the blocks can access this directly. So now I don't have to have all the expensive reads from global memory to shared memory, and then have to isolate the boundaries. Each of the blocks and each of the threads all read from one point, and that's global memory. And I'll show you how I did that later. Now I'm just sort of going over my general headaches that I had when I was developing this. And I found this was very fast. The second bullet here, the slow memory, that was only about 4 times faster. This was 17 times faster, to quote exact statistics. So that was obviously enough of a reason to motivate me to keep with the direct memory. So this is not always the case. In some applications, obviously, global memory will be more expensive, but in my particular situation, it was better to go this way. So I'm currently using global memory, and the next step I want to use is texture memory. And I admit I'm not an expert on this whatsoever. I'm still learning, but I know that this is a more optimal route to go. So that's the next thing I'm going to explore. So here I give a very rough pseudocode for how I did this. All of these bullets were performed on the host, on the CPU side. So we're not even into the kernel yet. We haven't actually called the GPU yet and are operating on that. So, oh, and by the way, this is another important decision for you. Do you stay with what your code is programmed in, which could be Fortran or some other language, or do you want to reprogram all of it in C? I decided to reprogram everything in C, and I was motivated for different reasons. For one, the way that memory is stored in Fortran and C are orthogonal to one another. C is row major, where Fortran is column major. So I didn't want to deal with that, and besides, it seems so much more natural to program the host code in C, since the CUDA code is just a derivative of C. To me, that was my logical decision. So that's a decision each of you are going to have to make. I know that some of you have legacy codes that your research groups have written from years past, and it could be in Fortran 77, Fortran 95, or some other language, C, C++. So it's an important decision to make. Some of you may decide to isolate the most expensive parts of your code and only recode those in CUDA and simply call from Fortran or any other language you're using. So depending upon how much code has been written already, that will motivate your decision. So anyway, to get back on track with the pseudocode, this is what I did top down. I first used dynamic memory allocation to allocate all of the pointers on the host side. I set my initial conditions and the boundary conditions on the CPU, since that's relatively inexpensive. I set up my coefficients for my coefficient matrix for the temperatures. I did that because these remain constant. These are stationary for all iterations. And I allocated the device memory, and you learned how to do that in the class, and also how to copy all variables to the device. So now I'm going from host to device. I set up the execution configuration where I give the dimensions of the grid and the dimensions of each block, and I give the actual code for that next. And then the iteration loop. This is also very important, is I found the best way to create an iteration loop using CUDA is to have the iteration loop itself written on the host side. There's a very important reason for that. Blocks cannot be synchronized. So that's a very big problem. And that also motivated the red-black, actually, because you can't use classic Gauss-Seidel. You have to use a parallel algorithm, because in Gauss-Seidel, there's a recursion where you need to use the old and the new simultaneously. But if you're trying to share that among blocks, there's no guarantee that an adjacent block has been updated to the same point as this other block. So it's a very bad way to do it. Everything will be out of sync. So it's easier to just use a parallel scheme and use the iteration loop on the host side. So what I did was I first called the red kernel, as I called it, redkernel.cu, and that updated all the red. That came back to the host, and coming back to the host tells you all blocks have executed. Irrespective of what order they executed in, they have executed, so you know that during the execution it was asynchronous, but now it's been synchronized since it's back to the host. So all red squares have been updated to the next iterate n+1. Then you call the black kernel, which does the same thing. It takes the red and now updates the black to n+1, and then you just iterate on this from I=1 to iteration max. So that's one of the most important things about the algorithm, is knowing to call. So in other words, for each iteration, you're going to have to call the kernel every step. So it's really impossible to actually have an iteration loop on the device side. It's better to have it on the host side. And then the last step, naturally, is just to copy the final results upon convergence back to the host side and then post-process, whatever plotting program you'd like to use. So here's the actual code. This I cut and paste from the source code that I wrote. The first is the execution configuration, and the dimensions of the block are no surprise, block size by block size. But the dimensions of the grid are special. This was, again, a design decision that I had to make. I decided to make the internal cell geometry, where we have Imax and Jmax, which is the maximum cell count in both the x and y direction respectively, to be divisible exactly by the block size. So I show this graphically in one of the following slides to be able to visualize and orient yourself with what I'm talking about. But so when you set this up, either you need to decide a block size that divides evenly into your given grid, or conversely, choose a grid that's evenly divisible by your block size. So for efficiency, I chose a block size of 16, held it fixed, and then I just varied my grid and made sure that that was divisible by 16. And then here's the iteration loop, and that's it. This is the entire iteration loop. It fits on one part of one slide. So I go from iteration 1 to iteration max. I call the red kernel, updates the red. Call the black kernel, updates the black. That's it. So and you just iterate until the end. So, and by the way, this is again all on the host side. So, and this is an issue I've been talking to some of you about, is how do you make the connection between your physical mesh and your GPU mesh, or your GPU grid that's filled full of thread blocks. So this is what I did. This is a mapping, actually, that I think you probably covered in class, I think. This is a way to convert the two-dimensional indices for the blocks and threads into a one-dimensional index, a global index, if you will, that travels along the entire grid. So this way you can map, in a global sense, each of the thread indices for all the separate blocks. And then, as you'll see in the next figure, this is all I had to do. I had to stagger the thread indices by 1 to convert from my GPU grid to my actual CFD grid. So let's illustrate this graphically. So here we have our checkerboard, right, because we're using red-black. The gray are the boundary cells, okay? And as you can see, they're labeled IMAX, IMX, and JMX. And I also add 1 on each side to make it IMAX and JMAX, which you'll see why later as I show more source code. And this is the connection. This is a one-to-one mapping between the GPU grid and my CFD grid. And that's how I did it. So I thought, and again, this is another design decision you're going to have to make when you create the code. How are you going to relate the threads to the grid cells or to your mesh points? So I decided the most logical way to do this would be to assign in a one-to-one way each thread to each grid cell. So throughout execution, each thread is responsible for babysitting that one grid cell. It does all the updating, it does all the calling to find all the adjacent values for local support, etc. So that's it. So you find that if I'm using block 0, 0, it maps, using the mappings that I showed on the previous slide, to this cell in the upper left-hand corner. And then the last cell will map to this last thread. And by the way, this is another decision I had to make. This is obviously different than classic CFD grid notation. Most of you may be used to the IJK notation, which starts at 1, 1, 1, right? And if you're using a two-dimensional grid, it typically starts in the lower left-hand corner. Well, I decided to use a matrix or array notation instead, because it was less of a mapping issue. So then I'm essentially starting almost in the same corner. It just seemed natural to do it that way. So that's all I do. So there's the mapping between the GPU and my actual grid. So now I'll go over some of the source code that I used. And again, all in one slide, I can fit the entire Gauss-Seidel with successive relaxation. So this is a key part here. This is from the red kernel.cu. I also had a black kernel.cu, which is absolutely identical, except this is different. Here, I take the row plus the column, and I use the modulus operator. So I'm essentially asking, is the sum of these two exactly divisible by 2? If that is true, then it's a red cell. Then update the red cell. In the black kernel, this is 1. Right? And that's it. Some of you may have seen this. This is just, this is really nothing new. This is a classic red-black algorithm. What's new is this. So if you're using a serial code, you have nested for loops here, right? You would go through all I and all j. Well, now you no longer do that. You simply write one equation, and that one equation is understood to take on all values of the threads, because it's a SIMD operation, single instruction, multiple data. Each of this is going to be executed by each thread in each block in the entire GPU grid. So I should probably explain this mapping. This was actually performed initially on the host side. All of my arrays are 1D. Again, another big decision you're going to have to make. Some of you may be using multidimensional arrays, 2D or 3D. I decided for simplicity to keep all arrays one-dimensional. So since I'm using a two-dimensional domain, I had to use an initial mapping to map from ij to some k. And this is what I do. I map from row column to k, and I multiply by Imax. If you do this, then you get a unique one-to-one mapping, and all the numbers are in numerical order. So that's, again, pretty standard if you work with CFD or any type of numerical analysis. So what's happening here? This is just a code version of the equation I gave earlier. But what's happening in here, each of these are the mapping that I used, but I increment. So I go west, east, south, north. I just increment in each of my cardinal directions. Remember, I'm using local support, so I only need to offset by 1 in each direction. That gives me the sum. I take the sum, and I divide it by AP, which I defined earlier was the sum of all the coefficients, which was actually calculated. You don't see it here because it was calculated on the host side. And then I use my successive over relaxation here to accelerate convergence, where omega is taken to 1.85, so typical value between 1 and 2. And then that updates that cell for that k. So, and that's it. So here are the results you get from that. And again, you can compare this to either the analytical solution, because this problem does have a closed form solution, which is nice, or you can compare it to the CPU version that you've written, which is what I did. And then you get this. You get these nice temperature contours. And remember, the boundary conditions, it was 0, 0, 0, 1. So we expect, in a heat conduction sense, for the waves of heat to flow this way until it reaches steady state. So if this were a transient problem, this would all be blue initially, and it had a red line, and then you'd see the heat flow through until it reaches steady state. But it is a steady state problem, so I just wiped out the time derivative beforehand. And that's it. So that is an entire example of using CUDA to solve a second-order linear PDE. It has a physical application, but I try to keep it general enough to where no matter what PDE you're using, that would be how you do it, assuming that you're using a stationary iterative solver. Because that's what I use. Some of you may be using an optimization-based solver, non-stationary solver, like Krylov subspace method. I know Professor Menka discussed some of those on Monday in the GPU panel, GMRes, or something like that. So But this tutorial was more along the lines of stationary iterative solvers for a matrix. So now, that was a simple baby problem. Now let's hit the real problem. So yes, question? Sure. Yes. Yes. Okay. Oh, okay. Oh, okay. Yeah, so for the first question, how did I remove the conditionals? My rationale for using conditionals in the first place was that I was copying my full array. Actually, I'll go back. Probably graphical illustration will help you out. Or, yeah, there. Okay. So all of this is copied from the host to the device. Boundary conditions and internal data initially. In my initial algorithm using shared memory, I would say, okay, well, this is going to act, if you're familiar with MPI, I'm trying to segue from one to the other in a decomposition sense. Let's say each of these are processors, okay, or tasks or ranks if you're familiar with MPI notation. This block governs this 2x2 subset, this block governs this 2x2 subset, etc. So if I'm doing that, I would have to copy these using each of these threads, a 4-to-4 mapping, but then I would have to copy a halo of boundary cells. But the way I designed this is that, okay, look, okay, I was watching your reaction, you see what I mean? Or, okay, well, the reason you have to do that is because just like in MPI, if you're doing any type of parallel domain decomposition, instead of computing the whole thing on one processor, you cut the problem into pieces, distribute it, and then have each processor work on that subproblem. In order to do that, you have to have local boundary conditions. These are the global boundary conditions. So you would need local boundary conditions in order to integrate this subarea. So the if statements are as follows. I have only enough threads to handle the internal cells, but I also need to handle the boundary conditions. So how do you do that in a CUDA sense? I use if statements to isolate these threads and then say increment up, grab these, increment to the right, grab these, increment down, grab these, increment to the left, and grab those. Okay? There's another alternative. You could declare enough threads for the whole grid, right? But that I felt also was computationally inefficient because that means these threads that would correspond to the global boundary conditions would be idle 95% of the time. So that's a waste of resources. The way that I designed this was that all threads would be active constantly. Whether they're grabbing boundary conditions or computing themselves, or the way I decided to do it was to have them just locally grab each of their neighbors in direct memory. So now to compare this to the way I did it, before I had this in global memory. Well, still I have this in global memory. But now instead of using if statements and sort of a domain decomposition format, I simply say all of these threads go into global memory and grab whatever they need. It's all there, they just grab whatever they need. So they're able to grab the boundary conditions, they're able to grab their internal nearest neighbors, etc. So hopefully that answers your first question. The second question you said about computational cost. I programmed a GPU timer into my code, where I start the timer and I end the timer. I don't know if you covered that in class, a GPU timer. Okay, so I should have brought code for that, but you can program a timer where you can start the clock and end the clock, so to speak, so you're timing only kernel execution. I admit I did not time per kernel call what the computational cost is. So I don't know for sure what that would be. So yeah, okay, yeah, that's a good question. Maybe Professor Hu can answer that better than I can. But for this particular code, I did not do any timing tests or profiling to see. I looked at what was the bulk time per, for the full integration time. So hopefully that answers all your questions. So,
location overhead is significant, but obviously, you still got benefit. Like, we have a similar problem with LBM, and the LBM application is about less than 20 times speed up rather than 100, partly because of the kernel location overhead. So you're probably running into the same thing here.
Yeah, I would say so. And as I said before, I'm sort of stuck with this algorithm because I have to call it every time step. There's no way, because of the blocks being asynchronous, I have to wait until the kernel is finished. All blocks in an unassumed order have to execute first, and then it has to return to the host. Only then can I be confident that each of the blocks, and therefore each of the threads have executed, and therefore have updated all their respective cells. So that was my rationale for having to do it that way. I was stuck with that. So now we go back to the main problem. So here is what the heat conduction equation was before. The energy equation reduced down to the Plotchian of a scalar 0. Well, now we have to include all the terms, and we also have the conservation of mass and conservation of momentum. Some of you may be familiar with this. This is not an integral part of the lecture. I'm just sort of segueing into the problem. This is what we're trying to solve now. These are the full governing equations for a compressible viscous fluid. So we have to solve these somehow on a GPU. And that's going to be tough, and we're debating on how to do that exactly. So there's the problem. But how do we discretize it? Well, here's the starting point. At least we have numerical methods first, and then we'll be able to figure out a way to use GPUs. So we're going to use the fractional step method. So here specifically, we'll be using it for incompressible flow, but here we make no assumptions about the density. We keep that on the inside. So what is the fractional step method? This may help some of you, actually. Some of you may be using this type of algorithm. In the fractional step method, it's essentially a two-step process where we take momentum and we wipe out the pressure. H is going to be a collection of the convection and the diffusion terms, and then we include the pressure here, and then we have a divergence-free condition. Okay? So there's something I'm getting at, actually, and I mentioned it here, the pressure-Poisson equation. This leads me to the second reason why we chose to solve the Laplace equation first. In addition to being a convenient, easy problem to learn from, it has a strong connection in an algorithmic sense to this, because the Laplace equation is simply a zero right-hand side version of the Poisson equation, right, if you're familiar with PDEs. So the Poisson equation is just the Laplacian operator equal to a non-zero right-hand side. Now, you can't see it, but if you take these two equations and you solve for the velocity n plus 1, you eliminate it, actually, and then you'll find that this is the pressure-Poisson equation. Okay? And here's why. This is the main selling point to use GPUs. It consumes 70 to 95% of the CPU time. If you're using multigrid methods, which we've used before, then it's going to be 70% of the computation time. But if you get rid of multigrid, then you're going to have, then it's going to get up to 95% of the time. And if you're not familiar with multigrid, that's basically a way to accelerate convergence. And it lends itself very well to elliptic type equations, which are exactly this type. The Poisson equation is a PDE of elliptic type. So multigrid methods lend themselves naturally to that problem, which we've used in the past. And then, of course, we have the boundary conditions, which are just going to be hard boundary conditions again. Future velocities are equal to the same boundary velocity. And then we have a zero gradient boundary condition on pressure, which are pretty standard if you're familiar with CFD. So we solved this problem, the Laplace equation. We have a working algorithm, and now we need to implement it here to pare down this much time. And it's such a huge amount of computation time that we have to get rid of. So that motivated looking at the Laplace equation first to pare down that computation time. So now just the general conclusion. To summarize the results, we've developed a red-black SOR solver for a two-dimensional Laplace equation. And for this one, it was around 17 times faster using our direct memory, or global memory. And right now, we're in the process of developing the CUDA algorithm for large eddy simulations. So if you're familiar with that, that's a method to resolve turbulence in flow fields, where you... Okay. Yeah, so if you're not familiar with large eddy simulations, in a nutshell, that's just a good method to resolve turbulent flow fields, where you're exactly resolving the turbulent scales on the large scale, but then you're modeling the subscale turbulence eddies. So, and also we'd like to thank our collaborators, Professor Wynne Hu in the ECE department, and also John Cohen from NVIDIA. He's a guy at NVIDIA that's been working on red-black solvers and also multigrid and Navier-Stokes solvers. So we were almost done with our algorithm when we started talking to him and exchanged ideas, so that was very helpful. And their guidance is, of course, greatly appreciated. Yes, and of course, Professor Bankus. So I didn't mean to leave you out. It's understood that he's acknowledged. Yeah. Okay, there you go. Yeah, exactly. So that concludes my talk. So I'll take any questions. So any more questions for Aaron?
One thing that I really like about this part is that he also is demonstrating some of the computational thinking action. Right? He's talking about mathematical formulation, and then he's getting into this, which one is parallel, which one is not parallel, and boundary conditions, and those are the the first kind of things you're going to have to wrestle with. So shoot, questions. I saw some questions that came up.
Okay. Okay. Oh, right. Yes, you're referring. Okay. The reason that was for AP, which is the coefficients of the point, which is taken to be a sum of the nearest neighbor's coefficients. The reason I did that is because that's stationary for all iterations. So yeah, exactly. So it's simpler just to quickly add them up and you're done, and then you store them and then you pass them. So I would do a CUDA memory copy from host to device. Yeah, so that's why I did that. That's important to mention, and that's something I'm trying to stress. You want to have to make decisions as to what's worth keeping on the CPU and what's really slow enough to put on the GPU. And I had to wrestle with that. Like initially, I wanted to do everything on the GPU just to be safe, but then I realized that cost versus benefit sometimes it's not to your advantage to put everything on the GPU, especially if that's just a few floating point operations. It's free adds, right? So and it's stationary. So why not just quickly compute, store it, and pass it? That's what I did. So yeah, yeah. Okay. Okay. Sure.
Is the performance benefit saturated after a specific point in the problem size?
That's a good question. Yeah, so you're asking
repeat the question.
Okay. Yeah. So he's asking, is there a relationship between performance gain or loss versus the scale of the problem? So as I keep making the problem bigger and bigger and bigger, obviously the performance will go up actually. So is there some asymptotic value at which, or is there like a drop where it's some curve where performance goes up, and then it gets to a point where it starts going down? I haven't reached that peak yet where performance goes down. When I've ran these test cases, I find that performance just keeps getting better and better. Okay. Asymptotic. Yeah, that's a very good question. I haven't performed enough benchmark cases to find what asymptotic where it starts to plateau. That's a very good question though, actually, to see. It would take time because you would have to run all these on the CPU and run them all on the GPU and keep, in this case, all of my grids are sort of a factor of 2. I keep doubling, times 2, times 2, times 2, times 2. So each time it actually grows quite big. So I'll have to see. But I don't know yet. That's a good question.
In terms of comparing, say, this is sort of suite implementation of Gauss-Seidel.
Uh-huh.
Can you compare this to sort of to multi-grid on a CPU, see if
Oh.
multi-grid is the best.
Oh, yeah, yeah.
So, and then that's the way into, have you thought about doing multi-grid on GPU? And obviously multi-grid is probably implemented parallel. So,
Yeah.
what do you see happening there?
Multi-grid's better, and for this problem, it's faster. It is faster. Let me give you some numbers. I ran this code for a 1024 by 1024 grid, million cells, right? So on a CPU, this code took around 2 hours. And if you use this on a GPU, it takes 7 minutes. With multi-grid, that would be, on the order of seconds. I think it would converge maybe within 30 iterations. Multi-grid is very fast, very fast. But for this problem, see, it's problem specific. You can't always use multi-grid. So, but to answer your other question, so I'll summarize your first question. The answer is yes, multi-grid is better for this problem. But we've also, for your second question, we've also tried to look at multi-grid on GPU, but so far have been unsuccessful. We know algorithms have been developed using multi-grid, but we're still working on that. So there's still some issues to overcome. So I don't know if Professor Banka wanted to add anything on that. He's sort of a resident multi-grid expert. They have developed one, yeah. Yeah.
Aaron, you need to repeat Professor Banka's answer for the remote site.
Oh, okay, sorry. Yeah, he was saying that NVIDIA has developed a red-black multi-grid solver. So they obviously have much more experience than I do. They were able to rapidly produce one. We haven't been able to do it in our group yet, but as Professor Banka was saying, the issue is that when you do the execution configuration, you are immediately locked in with how many threads you're using. But with multi-grid, if you're familiar with the multi-grid algorithm, like a V-cycle, you start with a fine grid, and then you coarsen the grid successively, restricting errors and then solving, restricting errors and solving, and then you restrict to a very coarse grid, and then you prolongate or interpolate back to the finer grids, and that gives you a V-cycle, right? But the problem with that is as you use a coarser and coarser grid, that means you're having less grid cells. So that's less threads you're going to have to use. So some threads are going to be idle, and that gives you a performance loss. You have threads just sitting there. So we're not exactly sure the best way to implement that yet. So that's something that we're working on. So,
Okay. So these three, and then we're
okay.
have to cut
Yeah.
out.
Yeah, that's absolutely right. Yeah, that's something that I plan on in the future. So right now, everything, you're going to have to because large data, she's right. Large data simulations are extraordinarily expensive in both computational time and also in storage. Storage is a big problem. So, but ultimately, we want an algorithm that is parallel GPU. No, I mean, I don't know. Actually, I haven't really thought about a hybrid between different parallel architectures, but preferably we'd like to get away from MPI and use pure CUDA, and then use parallel GPUs, but we have to find a way around just having everything stored on one local GPU. So, good question. So, any other question? Okay. That's absolutely right. Yeah. Mm-hmm.
I got this error. It seems like if you index it in such a way that you had every set result over every other hop,
Mm-hmm.
every other cell,
Mm-hmm.
then you'd be able to eliminate the addition.
Yeah, that's possible.
Repeat the question. Yeah.
Okay, he's referring to a change in index. I chose this because to me this was the most logical way to do it, and it's sort of like a classic way to use a modulus operator. I did explore alternative ways to index. So his response or his question was that the way I have it written, it looks like there could be a better way to index this such that you're using every other thread. Is that what you're saying? Or every thread on every other cell. That's possible. You could do that. Yeah, initially I did not want. This is actually a good point. I have read that other people, especially a group at the University of California, San Diego, they were doing this, and he actually also developed a multi-grid solver. But he had some performance issues with his, and he was using also the modulus operator, and he complained saying the modulus operator was slow. But then he reported on his website that other groups said the modulus operator was fast on the GPU. So we're getting conflicting reports on how fast the modulus operator is. That's one issue. Is trying to use the modulus operator on the GPU, and the other is can we get away from the modulus operator altogether? So as far as logic, this is the fastest way to code it, but I did explore other ways to index. I just decided to use a modulus operator. So I did explore any others when I got the performance gain that I got. But as we, and going back to his question about the asymptotic performance, as we approach the asymptotic performance, then we may say, okay, we maxed out what we can do. Let's explore other options and tweak our algorithm, and that would be one of the areas that you can change. So
is there last question?
okay.
It's a completely general question.
Okay.
So if you don't mind, I would also like to one of those comments.
Okay. Okay. Okay.
We always compare GPU performance, according to what we saw in class, we compare GPU performance versus CPU execution time. That is good. Why we don't compare GPU performance versus, let's say, competitive with more cluster? I definitely understand the first point. I don't have a justification why not do the second point.
Yeah, I have thought about that myself, actually. And
Repeat the question.
okay, his question is, all the statistics and the boasting, I guess, about GPUs is that we take one GPU and we compare it to one CPU. His question is, why not take one GPU, which sort of acts like its own local cluster multiprocessor, to a true multiprocessor, a cluster of CPUs, like a cluster of 512 or 1024 processors. So I've also thought about that. I don't know why. I've never seen any comparisons between a CPU parallel and a GPU parallel.
Let me talk about that.
Okay, okay. Okay, yeah, so maybe you'll have some comments.
Okay, so for now, let's thank Aaron again.
Okay, thank you.
Good.